volcanoes are perhaps the most dramatic features on the Earth. In the last two lectures, we've looked at how the Earth's surface changes constantly as the continents move around. Volcanoes are telling us that something's happening inside the Earth as well. Volcanoes produce liquid. Here's something spewing lots and lots of liquid rock, which we call magma, all over the countryside. It's bubbling away, it's flowing in channels looking like rivers here, and it can flow very quickly. And here, it's even flowing over a cliff like a waterfall. Perhaps we should call it a lava fall. And these volcanoes pose one of the great puzzles about the Earth. Where does all that liquid come from? Now here we have what a lot of people would think of as a typical volcano, a kind of conical mountain. Now, curiously, that sort of mountain or volcano doesn't really produce much liquid. Liquid tends to ooze out of rather different features, like this crack here, this fissure, which can ooze lots of liquid. It trickles all over the place like this and bubbles away. The conical mountains of that sort tend not to produce liquid at all. They tend to do this instead. And furthermore, we tend not to get both types of volcano in the same place. We usually get either one or the other. So why are there these two types of volcano? Why are there volcanoes in the first place? And what are they telling us about the inside of the Earth? What we're going to talk about today is that kind of question, where this liquid comes from, why we have these two types. And it's only in the last 10 years or so that we've started to get good answers to those questions. Now, one thing is for sure, that the popular idea that we're somehow floating on a lake, underground lake of lava or magma is certainly not right. In the last two lectures, we showed that the outer 3,000 kilometers of the Earth, which we call the mantle, is certainly solid. Below that, there's liquid in the core, and the liquid in the core is iron, which is not what we see pouring out of volcanoes, so we have to find some other explanation for what's going on. The first clue is where volcanoes occur. And if we look at the volcanoes in the world, nearly all of them occur either near these big ranges of mountains down the middle of the oceans, which we call the mid-ocean ridges, and these are the places where seafloor is created by seafloor spreading, or they occur near these long, deep slots or trenches around the edges of the ocean basins, and these are where seafloor is destroyed. So it looks like the creation and the destruction of seafloor and volcanoes are all part of the same story. Well, let's start by looking at the mid-ocean ridges where seafloor is created. After all, these things have made 2/3 of the Earth's surface, and it's not so easy to look at these things because they're mostly underwater. One place we can look at them is on here, where they stick above the sea level at Iceland. This is one place where the mid-ocean ridge comes to the surface. So if we go to Iceland, what do we see? Here's some volcanoes in Iceland producing masses and masses of liquid rock, spewing out over the countryside, flowing incredibly fast. And you look at this stuff, this liquid, and it's really hard to believe that this runny liquid, when it solidifies, cools to make this rather dull black rock here, which we call basalt. Now, to try and convince you that that's what really happens, we're going to make some. Now, over here, I have my colleague Paul Beattie from Cambridge, and he's walked in with what seems like a sort of pizza oven. Well, how hot is it in this oven, Paul?
It's 1,300 degrees centigrade, which is the sort of temperature at which the rocks under most volcanoes will melt.
Right, so they take a lot of melting. That's about gas mark 96. Wouldn't do your pizzas much good, but I expect you have something else in there. What's actually in there?
Now, we've taken a lump of basalt lava, like this one that's come out of a volcano, and powdered it up so that we can put it back into the furnace. And I've got some of that powder sitting in a tiny little platinum crucible, like an egg cup there, inside the furnace so that we can take it out and look at it.
Right. So there's not much in there, and you'll see why soon. And I want to explain to you what's going to happen, because this will happen quite quickly, and you need to know what you're looking at. Bryson and I are going to open the door of this oven. You'll be able to look inside. This is the temperature of volcanoes you're looking at in this oven. Paul will then, with his tongs, produce this crucible like an egg cup, and he's going to pour the magma into this tank. It's going to happen quite quickly because Paul hasn't got long to get it out of the tank before it cools. He's put on these funny-looking dark goggles so that he can see inside. Bryce and I are going to put on these because we're not quite sure what's going to happen. Okay, everyone ready?
Ready?
Ready? Ready, Bryson? Go. That is magma. That is molten rock that Paul has poured into the tank. Thank you very much. Let's close this. So that magma, which has poured into the tank here, was immediately solidified. Let me pick out a bit. And here, this thing, this little pellet, is basalt. That is exactly the same as that rock we were looking at there. So that is how it's made. So the great characteristic of this basalt is that it is so very runny. And that's why when you go to Iceland, you're actually surprised. What you see in Iceland, here's what the biggest volcano in the world looks like in Iceland, and it's rather flat. It's like a sort of gentle dome. And we call these things shield volcanoes. And it's a gentle dome because this runny basalt runs all over the ground. It just dribbles all over the place. And it flows very far and very fast. And it really just cannot build itself up into a conical volcano. Now, it's so runny that it can actually pour out of the ground in fissures and cracks. Here is a long fissure or crack, and we're looking at lava pouring out of this thing. This is a slot. It looks actually rather like that slot on the table right at the beginning, although about 1,000,000 times more grand. We're looking at something a kilometre long there or so, and this stuff is just pouring out of it. Now, it could only do that if it was very runny. Another story which illustrates how runny it is in Iceland is this. They have boreholes into the earth to pick up hot water, and the reason it's hot is because it's close to magma, which is heating it, and from that hot water, they generate electricity. Now, when they first built this station, they drilled a hole into the ground, and what came out wasn't hot water, it was magma. Lava poured out of this hole, about 2 tons of it, totally swamped the whole thing, and they had to abandon it. Now they got it going again, and they can use water to generate the electricity. But the point I'm trying to get across is that it's so very runny. Okay, that's what happens in Iceland, runny lava. Now, in fact, most of the activity at mid-ocean ridges, of course, occurs underwater. That's why they're called mid-ocean ridges. And until very recently, we haven't been able to get anywhere near them. But in the last 15 or 20 years, we have been able to, using midget submarines, very small submarines, which are really just balls. They're 6 foot across, they're spheres, they will fit 2 people, and they can go down to incredible depths. And I'm going to show you some pictures from an expedition last year, a Russian and British expedition, to the part of the mid-Atlantic ridge, just west of Spain and North Africa. That was a submarine, and here we have lava at the sea floor with a sea anemone for scale, so you can see what it is. And as they move along, we see this thing. Now, here we are looking at a sort of pipe, and the camera's moving slowly up this pipe. These pipes can be as high as 10 meters. And out of the top of the pipe is pouring what looks like loads and loads of black smoke. And these pipes are called black smokers. Now, what are these things? These things are not volcanoes. And these were totally unexpected when they were first discovered in the late 1970s. And they were first found in the late 1970s in the Pacific by a colleague of mine. And he was looking out at the midget submarine. He saw these things and he thought, well, what is that? And they had on the side of their submarine a mechanical arm with a temperature probe. And he stuck the temperature probe into that black smoker and it started to melt. And they had a telephone which linked them up to the mothership at the surface. And he said, my temperature probe's melting. What's going on? And they said, no, you must be imagining it. That can't melt until it's more than 300 degrees centigrade. And he said, I'm looking at this thing through a perspex window. What temperature does that window start to go soft? And they said, oh, don't worry, that doesn't go soft till about 70 degrees. And he thought, all right, I'm getting out of here. So they went away and they redesigned their windows and they put temperature sensors all over their windows to make sure they weren't going to run into trouble. What was coming out was superheated water. Water at 350 degrees centigrade, and it didn't boil because of the huge pressures. What they were also able to do on that expedition was actually, with a mechanical arm, take a piece of a black smoker. These things, as I say, go to 10 meters high, but what this is a small one. And this is the only one I've ever seen. These are extremely rare. It's very, very fragile, so I don't really touch it. But I'll turn it round so you can see it here. And this has come from nearly 4,000 meters beneath the Atlantic Sea surface on the mid-Atlantic ridge. And it's like a little chimney. And I'm looking down it looks a pipe. It's a kind of hollow pipe. Now, how is this thing formed? It's actually made of sulfides of lead and zinc and copper, mostly. And it's formed by water circulating. What's happening is that water is percolating down cracks and fissures at the mid-ocean ridge through all the lava and getting really hot down below. It's getting so hot that it can actually dissolve metals out of the rock, especially metal sulfides. That hot water then comes up to the surface and it becomes cold. It cools, and those metal sulfides precipitate, and this thing grows around the pipe. This is rather like a stalagmite, which might grow on the floor of a cave. Now, absolutely huge amounts of water circulate through these things at the mid-ocean ridges. The entire world's ocean goes through these black smokers every million years. One of the things that they did on this expedition was measure how much heat was coming out of this water system over a region about 200 meters by 200 meters. So that's a sort of big cricket pitch kind of size. And the amount of heat that was coming out of that area was 3 gigawatts. Now, that won't mean anything to you. How much is 3 gigawatts? 3 gigawatts is about the energy produced by 3 nuclear power stations coming out of an area the size of a cricket pitch. I doubt if you could even fit 3 nuclear power stations onto a cricket pitch, come to think of it. A huge amount of energy is coming out of these things. About 25% of the heat lost by the Earth comes through these things. Amazing thing. And they will actually be important for later on in our story, so just remember about them. These are the black smokers. But what about the lavas? That's what we thought we were going to look at down on the mid-ocean ridges. And what they saw was lava, okay, but it was that sort of knobbly lava. And knobbly lava looking rather like this. This is one, actually. This is a knobbly lava from the bottom of the seafloor, and it looks rather different from this kind of basalt, which you see at the Earth's surface. Now, the way this knobbly lava forms, we can see on this very extraordinary film I'm going to show you now. Here we are looking underwater now. This is lava which is flowing into the sea and being chilled, and it's being filmed by some lunatic cameraman swimming around watching it. What happens is the lava forms a crust, and then it bursts like a balloon and produces a lump on the bottom, and a ball forms. And then it does it again and makes another one, and here's another one forming. And this thing produces blobs of lava on the seabed, which look like pillows, and in fact, we call these things pillow lavas. And they're quite important, actually, because what they do is prevent the lava flowing very far away from the ridge. And if that is actually the reason why the magnetic stripes on the seafloor, which we talked about in the last lecture, are so neat, because the lava can't flow very far. It's actually restricted to where the ridge is. Well, where does all this liquid rock or magma come from? Let's remind ourselves what happens at the ridges. Here's what happens at the ridges. The seafloor spreads apart and hot rock rises up underneath. The hot rock can rise up as it's solid, because it's hot, and hot rock can actually flow like potty-putty as it moves. But as it's coming up from great depth, it's reducing the pressure by an enormous amount. At depth down here, the pressure is something like 40,000 times the atmospheric pressure. And as it comes towards the surface, the pressure is reduced and the rock expands. As it expands, it's still got all that heat in it, because rocks are actually lousy conductors of heat. They're very bad at getting rid of their heat. So even though the rocks are coming up slowly, 2 or 3 centimeters a year, they still can't get rid of the heat. And because they've still got that heat inside them, when they expand, they melt. Now, we tend to think that when we melt or boil something, it's a matter of actually just heating it up. And after all, that's what we've just done in the oven. But actually, we can also melt or boil something by reducing the pressure. Now, we tend to forget that because we live our lives at constant atmospheric pressure. But now I'm going to ask Bryson to boil this water by simply reducing the pressure. And he's got a pump there to suck the air out. Here's a thermometer measuring the temperature. It's about 45 degrees in here. And as we reduce the pressure, what I hope is going to happen is that our water is going to boil. Ah, thank goodness. It actually does boil, and it's still 45 degrees. So the water has boiled without us having to change the temperature. Now, as you know, water normally boils, of course, at 100 degrees centigrade, and it's boiling here at 45 degrees just because we've reduced the pressure. That's all that's made it do it. Thank you, Martin. Now, we can actually melt solids also by reducing the pressure. It's a harder thing to do only because we have to reduce the pressure by great amounts, a huge amount. And we can do that with this rather remarkable device here, which is called a diamond anvil. Now, this is John Sowerby from University College, which is down the road here, and he's brought this thing in. Let me show you what's inside it first. What we have inside this machine is this. I'm holding in this hand a lump of steel with a diamond at the end of it. And that diamond has had its point filed a little bit flat. And inside this capsule is another diamond, almost identical diamond, with another point which has been filed off on it. And between the two diamonds, we can put our little sample, the thing we're interested in, and I put the top back on, and we can squeeze them together. And John is going to squeeze them together simply by turning this brass little knob. The point about this thing is that diamonds are two things that matter to us here. Diamonds are very, very hard. They're almost the hardest thing we know about, but you can also see through them. So as we've squeezed our diamonds together, we can look down between them with a microscope and see what's going on. And that's what this is, and it's rigged up to a screen. So in here we have a sample which John has cranked up to quite a high pressure. What is the pressure in there at the moment?
We're about 10,000 times atmospheric pressure.
10,000 times atmospheric pressure. That's equivalent to about 30 kilometers into the Earth. So we have our sample, and we've taken it 30 kilometers into the Earth, and it's solid, isn't it, at the moment?
Yeah.
So now I'm going to ask John to reduce the pressure. And I want you to watch the screen here. Here we are looking down the diamonds at our sample, and the little black bits are dirt on the diamonds. And that's actually quite useful, so we can focus it. Now, as John is going to reduce the pressure, we should see liquid start to form. And you'll see little blobs of liquid appear, with any luck, soon. Oh, there's one forming in the middle. And these little blobs are going to grow and grow as the thing starts to melt. And soon, I think you'll probably see liquid coming in from the side of the picture. So you perhaps want to start looking inside. Look at all these blobs forming now. More and more of this is melting. The liquid is starting to take all the solid. Here's some coming in from the edges now. And now it's nearly all turning to liquid. And here it is. The last bit is melting, and it's nearly all gone. Thank you. Splendid. That worked very well. So what we did in that experiment was melt a solid simply by reducing the pressure, not by changing the temperature at all. Now that, as a process, has been known about for quite a long time, and we've also known that that is what must be happening under the ridges. That the mantle under the ridges, which is made of this stuff here, as it rises to the surface, starts to melt. But the big breakthrough of about last 10 years has been to understand how the melt, the liquid, actually gets out. Now, why is that a problem? Let me show you what actually happens when we melt this kind of rock. What this picture shows you is what the rock looks like under a microscope. And the microscope is a type where the grains in the rock show up colored. So these colored objects here are grains in the rock. Now, before I show you the next picture, I want to explain what we're going to see. When you start to melt this rock, liquid forms around the edges of the grains. It's rather like picking up an ice cube. It's slippery around the edges. That's where the liquid starts to form first. And then as soon as the liquid forms, we cool it. We cool the rock, and the liquid immediately freezes to make glass, in fact. And the reason we do that is that in this sort of microscope, glass looks black. So when I show you the next pictures now, we'll see glass, or black, which is frozen liquid, around the edges of the grains. Here we are looking at the edges of the grains, and the black is liquid, or frozen liquid, which is glass. And the extraordinary discovery was this. Here's a little pocket of liquid, or glass, frozen liquid really it is. And no matter how tiny the amount of liquid, even if there's only the tiniest amount of liquid, these pockets are all joined up. You can see little black bits around the edges of these grains here and here, and they join up to the next pocket of liquid. And one of the most extraordinary pictures I've ever seen, taken with an electron microscope, and it shows what happens if you can dissolve the grains away. And someone found a way of dissolving the grains to leave behind the glass. And here you can see little tiny tubes of glass which join up all the melt pockets, or liquid pockets. And it looks like a beautiful sort of lattice network, almost like blood vessels. And now you can see the importance of this liquid being so runny. It's so runny, it can even flow through these tiny, microscopic little channels. And that was the first discovery which really helped us understand how this liquid reaches to the surface. Now, to understand how it gets out, I'm going to need a couple of volunteers, please. Let's have you, please, and yes, you. Right, and your name is?
William.
William, will you come this side? And David, good. Now you stand here. Now, I'll explain what this experiment is about. We're going to pretend here that we have grains, and the grains are either red or blue. These are solid grains, and we've started to melt this rock, and we've made liquid, which is this green material, which is around the edges of the grains and in the pockets between the grains. And we want to see, well, how are we going to get it out? Because if that's what we do, if we just start to melt the rock, the liquid forms, and it just sits there. How's it going to come out? Well, one way we might try and get it out is by squeezing it. So let's put this on top, this press. And I'm going to ask you, please, to press down on it and try and squeeze these. Now, if you squeeze it, you can see the water level really doesn't change. It's at the level of that green tape, and nothing much happens. Thanks. That's fine. Now, let's try it over here. If I put this on here, now, can you reach in and squeeze it down hard as you can? Oh, good. The water level rose right. Do it again, if you wouldn't mind, and just hold it down so we can all see. There. That's excellent. The water level rose up when you squeezed it. Well, perhaps you didn't squeeze hard enough. Would you like to try again? You have another go. See if you can really try hard. No, it really doesn't do it, does it? Let's just remind ourselves what it looked like here. Have a really big push now. Wow, right. Good. Well, thank you very much. That was kind of you. Why were they different? Let's have a look. If I take the tops off again, the difference between these two is in the grains. If I take a blue grain and a red grain, the blue grains I really can't squeeze much. They're really hard. The red ones are squishy. They can change shape. Now, down there under the mid-ocean ridges where all the magma is forming, we have hot rocks, and for the third lecture in a row, I find myself telling you how important it is that when rocks are hot and solid, they can flow, they can creep, they can change shape. That down there in the earth where it's hot, rocks are squishy. And even though they are rising up from deep down and the pressure is being reduced, the pressure is still so great that you can squeeze the rock and like a sponge the liquid comes out. And that's the secret to how the mantle can be solid and yet all this liquid comes out. Because as soon as you form any liquid at all, it's so runny, it just whizzes up these little cracks and fissures and tubes, like the blood vessels, and it gets out of the way. So it just doesn't sit around. That's how the mantle stays solid. And this was a mystery which was really only solved properly a few years ago. So far, all we've talked about is this runny liquid, this basalt lava that forms at mid-ocean ridges. I think it's lovely stuff. I could talk about it all night. But let's move on. I want to talk now about the other sort of volcano. The other sort of volcano occurs around the edges of the ocean basins, near these trenches. This is a map of the Pacific Ocean, and we're looking here at the edge at these long, deep slots called the trenches. Now, what do the volcanoes look like that occur near those? Let's look at this picture here of one erupting. This is what you see. Big explosions. Bigger and better even than Bryson's one on the front bench. And these explosive volcanoes are what you find all the way around the edge of the oceans where you have those trenches. Let's remind ourselves what we see in subduction zones. So here's our model of a subduction zone. We have here the trench, which is this deep slot in the water here. This is seafloor, and this is the land behind us. Let's remind ourselves what's happened. Okay, Vipin, let's move it. As the seafloor moves down, we get earthquakes here on the interface between the two plates. That's what these red flashing lights represent. Those are the earthquakes. I think we'll do that one more time. Ready? Thanks. Now, somewhere down here, magma is forming, and it's rising up towards the surface up here. And at the top, what we see is this, a line of volcanoes. And these are the things which erupt. They do. So, what's happening here? Why are we getting magma? If you think back to it, at the mid-ocean ridges, material was rising up to the Earth's surface, and that's why we got melting. Here, we're pushing material down into the Earth, and we're getting melting. Why is that? What's happening? Well, this is seafloor, which formed at a mid-ocean ridge, and it's cold. It's really cold compared to the mantle on both sides of it, here and here. So why is it melting? The secret is actually water. The rocks of the seafloor here have lots and lots of water in them. They're wet rocks. Why have they got so much water? Because these rocks were formed at the mid-ocean ridge. And remember I said to you earlier that those black smokers were important. We were going to talk about them again. Well, this is when. Because that water which circulates through the oceanic crust at the mid-ocean ridges gets caught up in cracks and fissures and can react with rocks and make compounds with water in. And so as the water is taken down with the rocks here, the water actually makes the rocks melt. This is what water can do. Wet rocks melt much more easily than dry rocks. And these rocks here can melt at a temperature as low as 800 degrees compared to the basalt, which would melt at 1300 degrees. That is why we get the magma. But there's another small complication. At the mid-ocean ridges, we're melting the mantle. That's all there is to melt. There's nothing else around. But here, it's not quite clear what's going on, and we don't really understand it. I have to be honest here, because there are three things that could be melting. We could melt the plate which is going down. That could be melting. We could get melting also from this little wedge of mantle between the two plates here. That might be producing some liquid. And of course, we could get melting from the plate on top. That could melt as well, and we're not quite sure what's going on. What we are sure, though, is that the magma which appears at the surface, the liquid rock at the surface, is much, much stickier than that runny basalt we've been talking about. And the stickiest magma of all appears where you have a continent on top of here, like, say, the Andes. Because if you melt the continental crust, you get incredibly sticky magma. The contrast is amazing. Let me show you over here. Here is a picture taken from the air of a mountain in California, and it looks like we're about a kilometer or two across here, and it looks like someone has dropped a huge blob of toffee out of the sky, and it's just gooped all over this mountain. It's kind of trickled over the side and just solidified. And this mountain, which is in California, is called Glass Mountain, and it's actually made of this stuff, which is volcanic glass or obsidian. And this is a sample here, which I got from the Natural History Museum. Now, this stuff is volcanic glass. Volcanic glass is simply liquid which cooled really quickly. It cooled so quickly it didn't have time to actually make crystals. And this stuff is so sticky that actually most of the time it never makes it to the surface at all, and it just cools underground and solidifies. If it cools underground, it cools more slowly, and it can make crystals, and it will make this stuff. And this is granite. And it's extraordinary, really, that this granite here, this white rock, is exactly the same in composition as this black glass I'm holding. The only difference is that this black stuff never made crystals, and this white stuff did. They're made of the same material. Now, as I say, this stuff is so sticky, it really hardly ever gets to the surface. If it gets to the surface at all, it gets there because it's had some help. And it gets the help from the water, which helped to make it in the first place. What water does under pressure in the ground is it dissolves in the magma. And when water dissolves in the magma, it makes it much, much runnier than it would be otherwise, and that helps it to actually get to the surface. But if it actually gets to the surface, then that same water which has helped it causes a lot of trouble, as we will see now in this next demonstration. Now I need a couple of helpers. I have you, please, at the end, and yes, I'll have you at the front. Now, your names are? Andrew and James. We're going to take James first. Now, are you left-handed or right-handed?
Left-handed.
Left-handed. So I'd like you to put your right-handed glove on. And what about you? You are?
Right-handed.
Right-handed, so you need to put on the left-handed glove. No, that's fine. You keep that on, and you keep that on. This is all very mysterious, isn't it? We'll take you first, and we have here a bottle. So I'm going to put it here. Let me explain to you what I want you to do, okay? I want you to take a firm grip of this bottle in your right hand, and then take the top off. I want you to take it off quickly and cleanly and take it right away. Is that okay?
Yeah.
Okay, let's watch you. Right. You're safe. Nothing very much happened, and actually that was what I thought would happen. Let me explain what happened here. The bottle had gas in it, and that gas dissolved in the liquid because the pressure was high. As soon as the top was taken off, the gas came out of solution, it made bubbles. But because this is actually a very runny liquid, the bubbles were able to escape. And they escaped really without any trouble. Thank you. Now, stay here for a minute. No, leave that. And what we're going to do now is look at a different bottle. Now, who has got the short straw here? Let me explain what I want you to do. A strong grip in your left hand. I want you to take the top off really quickly, all the way, cleanly, and then I think we better stand back a little bit. Okay? Bryson will clean you off. Go out there. Thank you very much. It was much better than I thought even. Now, why was this so different? The liquid inside that bottle was just much, much stickier. And once again, it had gas, and the gas was dissolved in the bottle. And when the top was taken off, the pressure was reduced, the gas came out, it made bubbles, but the bubbles couldn't get out of the liquid. All that happened then was the bubbles grew. They got bigger and bigger and bigger until they joined up. And then that changed from a liquid with bubbles in it to gas with bits of liquid, and the whole lot shot out. And it's made this foam, which has dribbled all over the place, and that's what some volcanoes do. They also make frothy foam. Bryson's got some here. Thanks, Bryson. This stuff is pumice. It's just froth, this stuff. This stuff is 80% air. That's why it's so very light. I can hold it in my fingertips. It really doesn't weigh anything at all. Thanks, Bryson. And this, I mean, it's great fun playing these disgusting demonstrations that Bryson produces, but they're actually extremely instructive. Let me show you how this demonstration helps us understand the eruption of a very famous volcano. This picture here is of Mount St. Helens in Washington in the northwest United States in 1980 before its eruption. What happened before the eruption was that the volcano inflated with magma. It came in from down below, puffed up the volcano like a balloon, and made the sides steeper and steeper until eventually it fell off. And a great big landslide took the top off the volcano. Here's the side of that mountain just falling away. And we're going to stop it there for a moment, because that is exactly like taking the top off the bottle of the fizzy, sticky liquid we were looking at before. Now what happens next is this. Here is the explosion. The insides of that volcano are just blasting out in this terrific, huge cloud. This was photographed by a photographer standing in the wood nearby. Unfortunately, the blast didn't come towards him. Otherwise, we would not have these pictures. To give you some idea of just how big this blast was, let me show you this picture here, which is the mountain before the eruption, and now the mountain after the eruption. This huge amount of material, the mountain had just been turned into dust and ash and gas and blasted over the countryside. The blast was incredibly destructive. In these next pictures, we're looking at the mountain in the distance, and in front of us is the remains of a forest. these things which look like matchsticks are giant forest trees which have been just blown over flat by that incredible blast that came out of the mountain. Here, these things looking like sticks are much taller than street lampposts. This is the remains of that huge forest. And after the volcano had kind of cleared its throat, as it were, by blasting out that stuff, the insides of the volcano just emptied into this huge, high eruption column which blasted its way up into the sky. Now this is perhaps one of the most beautiful kind of features that volcanoes can make, a very big, high eruption column. And in the last 10 years or so, we've made really a lot of progress in understanding what these explosions do and the kind of things that can go on. And for most of the rest of this lecture, I'm going to be talking to you about the kind of things that go on in these big explosions. Why are they a problem? Because this stuff coming out of the volcano is coming out as a very fast stream of hot gas and dust and magma and bits of liquid and all sorts of stuff. It's coming out at a few hundred meters per second. That's about the speed of a jet airliner. That's how fast it's coming out. But if I was just to throw something into the air at the speed of a jet airliner, it would go about 1 or 2 kilometers into the air, and then it would fall down. Now, these things go 20 or 30 kilometers into the air. They go much, much higher than they should. We're going to do an experiment now, which is going to help us to understand what actually goes on. This is a tank of water, but rather special water. At the top of the tank here is fresh water. And at the bottom of the tank is salt water, which is much heavier, it's denser than the fresh water, and there's a gradient between the two. This is to match the atmosphere. In the atmosphere, the air is much lighter at the top than down the bottom where we are here, where it's denser. At the bottom of my tank, I have a volcano, and I'm going to feed a stream of liquid into that volcano, which is colored red. And the liquid that's coming into the volcano is fresh water. It's the same density as the top of the tank, and it's a lot lighter than everything else in the tank. So you'd think that, yes, of course, this stream will rise up to the surface where it's got the same density as the surface water. Well, let's see what actually happens when we do it. So I'm going to open the tap here. Let's see what happens. Here it comes. And it's coming up, and it's not getting up to the top. It's going up about halfway, and then it's spreading out sideways. It's making a mushroom cloud. And this mushroom cloud is growing more and more sideways. It's not going up. Now that's surprising. How can that be if the liquid which is coming out is the same density as the surface of the tank, and it's much lighter than the density in the middle of the tank? What's actually happening in this demonstration is that as this stream of liquid is coming out from the volcano, it's sucking in water from round about. And of course, the water round about is denser than the stream of liquid coming out of the bottom of the volcano. And so that makes the stream as a whole denser, and it can't rise up as high as we expected at first. It can only get halfway because it's got denser by sucking in all this liquid round the side. And this process of fast jets sucking in whatever is surrounding them is actually very common. It happens all over the place. And this rather lovely demo here, demonstration, which produces these big mushroom clouds, is going to help us understand what happens at Mount St. Helens. Thank you very much. Now, this big cloud here, this big eruption column at the top also made a mushroom cloud. And the next picture will show what that mushroom cloud looks like from a distance. Mount St. Helens is buried in the middle of the foot of that cloud, and this thing is so big that it couldn't actually fit in a camera frame. And so this is a picture made up of lots of pictures which have been glued together to make this one. And this mushroom cloud rose up to a height of about 20 kilometers before it spread out sideways. Now, what's happening in this is that the hot stream of gas and rocks and magma coming out of that volcano is again sucking in the surrounding air, but the air, of course, is light. And the air is then heated by that hot stuff coming out of the volcano. So the air which is sucked in expands. And this is like tying lots of hot air balloons onto what's coming out of the volcano. So it rises much higher than would otherwise rise. So whereas that tank, the mushroom cloud, the stream went lower than we expected, here it went higher than we expected, the process is exactly the same, that both of these streams coming out of the volcano sucked in the surroundings, and that's what makes the effect. It so happens here that because the air which is sucked in is heated and expands, this goes up. In the tank, the liquid which was sucked in was actually heavy, which prevented it going higher. But the process is the same. Now, that's not all that can happen. I'm going to show you first one other beautiful mushroom cloud. Here's another lovely mushroom cloud from a volcano in Alaska in 1990. And here, again, is a very, very high, beautiful mushroom cloud which has spread out sideways. And we'll come back to this one in a minute because there's a surprise about this one. These mushroom clouds can actually do other things too. Let me show you one more sequence now in an eruption from New Zealand. This is what it looks like just as the eruption is starting, and I'm going to show you 5 pictures in the course of the eruption of this volcano. This is 3 seconds into the eruption. We are about 8 seconds, the next one's about 13 seconds, about 30 seconds. We have one more, I think, about a minute, and the last one is this one. This is about 2 minutes into the explosion. And what we see here is a big high column, just like we've been talking about before, which rose very high. But what's this? Down the side of the mountain, we can see a cloud of dust and ash and gas pouring off the side of the mountain. And these things are one of the nastiest volcanic features that we've ever seen. Let me tell you how they form first. They form because as this stream comes out of the volcano, blasting its way upwards, it sucks in the surrounding air, but the air only gets to the outside of this column coming out of the volcano. The central part of that column never sees the air which is sucked in. And that simply goes as high as if you were to throw it in the air. So the central part of the column goes 1 or 2 kilometers, and then it collapses. And it collapses and it zooms down the side of the volcano as a hot mixture of bits of liquid, ash, dust, gas, zooming down the mountain. And these are the things which can be so terrible. I want to show you now some pictures from a famous eruption in 1902. This is the island of Martinique in the Caribbean. And we're looking at the small seaside town of Saint-Pierre, and behind it is a volcano called Mont Pelée. And this erupted in 1902. The next picture shows what that seaside town looked like in 1902, just a pretty quiet little seaside town with boats in the harbour. Immediately after the eruption, it looked like this. It's totally gone. You can perhaps see the street plans, where the roads were in this town, but all the houses have gone. What caused this was this kind of cloud. Here we have a current of dust and gas and ash pouring off the sides of Mont Pelée, racing across the ground, searingly hot, and clouds are rising off this thing up into the air. When people came after this to see what was left, it looked like this. The whole town had been burnt, gone. There was really nothing there. And the next picture shows a rescuer who came the day after to see what he could do, and there was nothing that he could do. Here are some victims lying there. There are still things on the table which you can recognize, bottles, plates, and so on, which are unharmed. What killed these people was heat. It was simply the heat of that terrible cloud rushing down the side of the volcano. Now, the picture of the cloud that I showed you was taken 6 months later when it did it again, and it was rather a small one. We don't have any pictures of the actual cloud that did it because no one survived to take them. But the point I want to get across was the heat which did all the damage. And let me show you some astonishing remains that people found when they went to Saint-Pierre to see what was left. They found things like this. Here is a fork, which got heated up so much it just bent completely. Here is the remains of a candlestick holder, which is just completely folded up and crumpled in that heat. This is a bunch of nails. These are ordinary iron nails which just fuse together in the heat. And here is a plate. This is a plate which is still perfectly okay as a plate, but it just got so heated up that it's just changed colour around its rim here. These things are extraordinary. These are bottles which were standing up and just changed shape. They just completely went soft in the heat from that dust cloud. And perhaps the most remarkable of all the remains that I've got here is this. This is a watch. we've no longer got the hands of this watch because they just melted. But those melted hands burnt themselves into the enamel coating of this watch, and you can see the time, it's 8 past. And that was the time of the eruption in 1902. There was only one survivor of this eruption, and he wasn't discovered until 4 days later. This was him. The one survivor was a murderer, and he was in jail, and he was condemned to death anyway. And he survived. He survived because his dungeon was underground, and it had a tiny opening, only this little window here, and that protected him from that terrible searing heat of the dust cloud. He was pretty badly burnt, but he was rescued 4 days later, and then he was reprieved. And he spent the rest of his life in a traveling circus wandering around telling his story. Now, to help us understand that kind of thing, what happened at Montpellier, how those currents which run down the mountainside work, we have another demonstration over here. And I need a volunteer, again, please. Let's have you, please. Thank you very much. And your name is? Chris. Chris. Now, I need you to stand here, and I'm going to explain what we're going to do, because it has to be quite slick, this, to get it right. We have a tank of water, and at this end of the tank here, I'm about to pour some alcohol. That's all that is. The alcohol will make this liquid at the end of the tank lighter than the rest of the water in the tank here. What I'll then do is pour in this stuff, which are just some solid grains, and the grains, of course, are heavier than the rest of the tank. What I'm going to ask Chris to do is to take this thing, this stick, and to stir it the whole time. It's quite important it stays stirred. So I want you to stir. I'll pour in that, then I'll pour in this, and then I'll tell you what we're going to do next. So will you get stirring while I pour this in? Okay, fairly vigorously. Keep stirring so it's nicely mixed up. Right, that's it. Good stir. And keep stirring hard while I pour in this. Okay. Keep stirring. Mix it up nicely. A bit more vigorously, perhaps. That's it. And in a second, I'm going to say stop. Please stop and lift it out. Lift your stirrer out. I'm going to open the door and let's see what happens. What we have here is a mixture creeping along the floor of this tank, which has heavy particles but light liquid because of the alcohol. As it's moving along, the heavy particles are settling out. And the light liquid that remains, of course, is starting to rise up. And it may not even get to the end of the tank. It should get somewhere round about here, and then it'll stop, I hope, and start to rise up. It looks as though it's stopping now. And then the cloud is rising up towards the surface. And when it actually gets to the surface, it might even continue going, but along the top of the tank. As it goes, I don't know, I can't see it from here. So it looks like a mushroom cloud now at the top of the tank at the end of that flow. Thank you very much, Chris. So that is the kind of thing we were seeing here at Montpellier, this hot, dense mixture of bits of rock fragments, ash and so on, creeping along the ground, very, very hot, but it doesn't go on forever. It stops and then it rises up to make this great big cloud. And now, let's return, next picture please, to that mushroom cloud in Alaska, which I said had a bit of a mystery to it. When we look at it, it's a beautiful cloud, and here at the bottom of the cloud, the volcano isn't there. It's over here. The volcano's in the wrong place, or rather the mushroom cloud's in the wrong place. What happened in this eruption was that it belched out a hot mixture, a hot, heavy mixture of bits of rock fragments and gas, which crept down the side of the mountain, and then at the end of its flow, it took off. And the mushroom cloud formed at the end of the flow, just like it did in that tank. And that's what made this rather beautiful mushroom cloud in Alaska in 1990. Now, explosive eruptions of this sort can throw absolutely huge amounts of material into the air. The biggest one we know about, or rather the fastest rate of eruption that we know about, comes from a volcano in New Zealand in AD 186. And this eruption threw into the air 100 million tons of rock per second. That sounds so odd. Let me say it again. 100 million tons of rock per second came out of this volcano. How do we calculate that? We calculate that because we can look round about at the volcano at all the stuff that was thrown out, how far it got, how big the pieces were, and so on. And that's what volcanologists do, and that's how they work out the rate at which the stuff comes out. How do we know it was 186 AD? Well, we can date the trees all around it. This thing destroyed the forest roundabout, and we can date the trees. We can't date it as accurately as 186, but we know it was about then. The reason we think it was 186 is an astonishing one. That this eruption, which happened in New Zealand, which is really the other side of the world, it's right down here, that eruption made the sky go pink in China, which is here, and also in Rome, which is here. Now, in 186 AD, no one lived in New Zealand. No European had been there. Even the Maoris, who were there before the Europeans, had never been there. China and Rome didn't even know about each other. They certainly didn't know about New Zealand. The historians in China and Rome both recorded it. They say, we don't know what's going on, but the sky's gone a funny color. And it was much later this century that we were looking at these records, combining it with what we knew about New Zealand. We thought that was what was going on. And it wasn't that long ago that a similar thing happened. In 1883, here in Indonesia, there was another enormous explosion of a volcano called Krakatoa. And that made the sunsets go spectacularly red in London, here. And in this book here, I'm going to show you some drawings made of the sunsets in London in 1883, 6 months after the explosion of Krakatoa. And they were so spectacular, these sunsets, that this person drew a series of crayon pictures just to get the color of the sunset at Chelsea, which is just a mile away from here. And here's what the sunset looked like at 4:40 in the afternoon. Here is 5 o'clock, and here is 5:15. And these sunsets were so spectacular, they were recorded in London. And the message is that this stuff which is thrown so high up into the atmosphere by these volcanoes can travel right the way around the world, and the dust is actually what makes the sunsets appear so different. Now, let me show you one more example from an explosion of Mount Pinatubo in the Philippines in 1990. This one produced such a huge amount of stuff that we could see it from space. This is a view from a satellite. The red outline here is the island of Luzon in the Philippines, and the yellow cross here is Mount Pinatubo. It exploded, and we're now going to show you a series of 3 pictures to show you how that mushroom cloud grew. Now, this is 1 hour after the eruption. This brown cloud here is the top of a mushroom cloud. We're looking down on it now, and the brown cloud is the mushroom cloud. The white cloud is just ordinary cloud, which happened to be around anyway. And now this is 2 hours after the explosion, and the last picture here, 3 hours. The cloud has come all the way out to here. And this cloud was 800 kilometers across, just 3 hours after the eruption. This explosion of Mount Pinatubo sent also 20 million tons of sulfur dioxide into the atmosphere. Now, sulfur dioxide in the upper atmosphere combines with water vapor, and it makes little droplets of sulfuric acid. That sulfuric acid cools the lower atmosphere. And as a result of this eruption, the average temperature on the Earth dropped by 0.5 degree centigrade for 2 years. You think, so what, 0.5 degree centigrade? Who cares? When I tell you that 20,000 years ago, when we were in the middle of an ice age, the average temperature in the world was only 4 degrees colder than today, you can see that playing around with temperature at 0.5 degree or so is really quite a dangerous thing to do. And a lot of us now have a suspicion that these big volcanic explosions, and there have been many which are a lot bigger than this, that these big explosions can actually affect the climate. And the other big problem with these big explosions is they produce ash. This dust falls to the earth here, and this Pinatubo landed on this aeroplane and made it sit down on its bottom. There was such a huge amount of ash fell out of the sky. This is a picture of a house on the flank of the volcano. The house looks as though it's covered with snow. It's actually about 1 foot of volcanic ash which just fell on this house. And at Pinatubo, unfortunately, this eruption coincided with a big tropical storm which produced tremendous amount of rain and turned this ash into mud. And rivers of mud covered the place. This is from an explosion in Colombia. Here are animals struggling through the mud. They survived okay. Here are people also struggling through the mud as these rivers of mud break through everywhere. Here's a little boy who was rescued from the mud. He's okay, he survived. But this mud is really pretty nasty stuff. It can sweep away whole villages, towns, bridges. It causes a lot of trouble. Now, what we've done is we've talked about volcanoes at mid-ocean ridges and at trenches, and nearly all the volcanoes in the world occur in those two places. But I can just feel someone in the audience saying, well, what about Hawaii? Now, Hawaii is perhaps the most famous volcano in the whole world, and it's right here in the middle of the Pacific Ocean, here. Absolutely a long way away from any plate boundary. What's that about? Let's remind ourselves what happens beneath the plates. Beneath the plates, there's hot rock, and it's flowing around like potty-putty. It's moving the whole time. And occasionally, you get a hot current of rock, which is coming from deep down in the earth, and it comes up towards the surface, and it's a little bit hotter than the surrounding mantle. It's only about 200 degrees hotter, which isn't much, considering the rest of the mantle is at 1,300 degrees anyway. But that little extra heat, the little difference in temperature, is enough to cause some melting at the base of the plate, at the bottom of the plate. And that melting, or magma, will actually come to the surface, and that's what Hawaii is. And we call those things hot spots. That's what they look like. But I want to end with something else. All this volcanic activity, especially the volcanic activity at the trenches, is dumping stuff on the continents. Volcanoes at the trenches can make the continents grow. We've heard a lot about these continents. We've talked about them moving around the surface of the Earth, and we've always just regarded them as passengers sitting on the plates. And the biggest volcanic eruptions, all the big explosions we've been talking about, happen because melting continental crust produces very, very, very sticky magma. So what are these continents anyway? Where do they come from? How do they work? What happens to them? That's what we're going to talk about next time, and we'll see they behave very differently from the seafloor. Thank you. For a booklet about the lectures or a video pack which includes the booklet, please send a cheque payable to BBC Education to BBC Education, Bankside Business Services, Unit 2A, Faraday Road, Newbury, Berkshire, RG 142AD. The booklet costs £3.50, the video pack is £29.